Hi, all CHEMMaster YouTube followers. So here in this video, we are going to discuss cycloalkanes. So unfortunately, we have lost our live session on cycloalkanes in 60 minutes. So that's why I decided to give the lecture as a recorded video. So you can get basics to advanced concepts on cycloalkanes in 60 minutes, where we are going to analyze typical examples which will be very useful for your competitive purpose. So watch the video completely to get the best conceptual analysis. Okay, right, and already we have part 2 on cycloalkanes. So watch it after watching this video as a part 1. Okay, right. We know that cycloalkanes are having great importance in organic synthesis because we can see natural products are having cycloalkane rings. Okay, so from 3 member to 7 member, 8 member, or macrocyclic rings. Okay, so we can give the examples as carbohydrates, where you can see a 6-member ring with heteroatom oxygen, that we call it as pyranose. Okay, so like that we can also see steroids. Can you give the best example? Cholesterol. Okay, so like that the cycloalkanes, or simply we can say saturated organic rings, are having great importance in medicinal and also in natural products. Okay, so that's why they are having a great importance in competitive purpose also. Okay, and here we can say that after the benzene, cyclohexane having the second most importance in organic synthesis, because it is having a wide variety of applications in medicinal purpose, and also we can see in synthesis of various organic compounds. Okay, right. Now the first point here, we are going to look at the stabilities of cycloalkanes. Here is a question: which is most stable? Is it cyclopentane ring or cyclohexane ring? So here, most of us, so who know the basics, will simply choose cyclohexane is most stable than cyclopentane. But in ancient days, according to here Bayer's strain theory, okay, according to Bayer's strain theory, cyclopentane is most stable than all other saturated organic rings. So how he predicted? Based on the bond angles. So we know that ideal bond angle for sp3 carbon, that is 109 degrees 28 minutes. If a sp3 carbon attains 109 degrees 28 minutes bond angle, then that carbon is in highest stability. Okay, so here when you consider the bond angle in cyclopentane, just write 108 degrees, whereas cyclohexane is having 120 degrees. Okay, so here you can see only 1 degree difference can be observed, here almost 11 degrees difference. Okay, so due to that, Bayer's predicted that cyclopentane is more stable than cyclohexane and all other saturated organic rings. Okay, but it is absolutely wrong, because not only the bond angle, other aspects are there which influences the stability of the rings. Okay, so here we need to consider various factors which affect the stability of the ring. Okay, right, here the first we consider ring strain. Okay, so ring strain is simply is the sum of angle strain, okay, and torsional strain. Right. So what is torsional strain here? So simply we can give other name of it as eclipsed strain. Okay, right. So the first case we need to look at the angle strain. Okay, you may have the concept of it, so don't worry, watch it again. Okay, right. So just look at here. We can start from the 3-membered ring. Okay, now just draw the most used rings here till 2, 7 or 8-membered rings. Okay, 7-membered ring, and here 8-membered ring. Okay, now just try to find bond angle here 60 degrees, here 90 degrees, here 108 degrees, here 120 degrees, here 135 degrees, here 140 plus degrees. Okay, right. And in all these rings, so cyclopentane is near to the ideal bond angle. That's why we are predicted that cyclopentane is more stable. But here other aspects are involving in deciding the stability of a ring. So as we look at here, eclipsed strain, and other strains we can see ring strain, and second one we can give steric strain. Okay, so we discuss each and every one here. So now we need to look at the torsional strain. We know what is angle strain. Now we need to look at torsional strain. Okay, right. So just know the basics of here each and every term which relates here, and they will be helpful for you in solving typical and advanced questions on cycloalkanes. Okay, right. Now torsional strain, or we can call it as eclipsed strain. So just remember that whenever the groups or atoms on adjacent carbons, okay, adjacent carbons or just parallel to each other, okay, if they reside on each and so simply here just remember, so if the two groups or onto each other, that means if you look at the bond angle, it must be 0 degrees. Okay, so in this case we can call that parallel positions of two groups as eclipsed. Okay, right. And here, so whenever the two groups or atoms on adjacent carbons or parallel to each other, then there will be the possibility of some strain, and we call that strain as torsional strain. Got it? Okay, right. And here we need to look at some of the examples and how they contribute for the torsional strain. Okay, right. Here just take it hydrogen and hydrogen. If two hydrogens are eclipsed each other, right, and we consider this interaction as eclipsed interaction. Okay, right. And for example, how they contribute to the particular ring. So just to say in kilojoules per mole, and in another case kilocalorie per mole. Okay, right. Now for this, in kilojoules per mole, 4 kilojoules per mole of energy, extra energy is added to that ring if the ring has one eclipse of 2 hydrogens. Got it? Just remember that. And in kilocalorie per mole, 1 kilocalorie per mole energy is added if one eclipse of 2 hydrogens is observed. Okay, right. And next case, hydrogen and methyl group, right? And for this, so it is contributing 6 kilojoule per mole. In calories, kilocalories, it is 1.4. Okay, and it is also, we can consider torsional strain or eclipsed strain. And if we have 2 CH3 or completely eclipsed, Okay, so in this case they contribute 11 kilojoules per mole of energy to the ring, and in kilocalories it is equals to 2.6. Okay, if the two methyl groups are in Gauche position, just take it, Gauche position, they contribute 3.8 in kilojoules per mole and 0.9 in kilocalorie per moles. You may get the questions in your competitive examinations based on these interactions. Okay, so you need to have some basics, or you may give the values in your examination. Okay, so you need to find the number of Gauche interactions or Eclipse interactions. Based on them, you need to find the energy of that particular conformation, and by that you can predict which is stable or which is having highest energy. Okay, right. And here, so just move into the some deepest basics here. You may already know it, but look at here, which is what is eclipsed, and how the eclipse interaction is observed and how Gauche interaction is observed. Okay, you can simply understand by looking at Newman's projections. Okay, just try to practice Newman's projection. Okay, I'm just giving x here, right, and in another case x, right. So if the two groups are completely relayed on each other, or simply say they are parallel to each other, so this projection is considered as eclipsed. Okay, right. In another case, just try to take it. Right, here is the x. Now, so here this, okay, so this projection simply gives Gauche interaction. Okay, and next one we can see, so this interaction is simply considered as staggered. Okay, now when you find these interactions, you need to add that much of energy to that particular conformation. Okay, right. And here, as we said, torsional strain and bond angle strain leads to ring strain. Okay, so ring strain is highest in cyclopentane when we compare with cyclohexane. That's why cyclohexane is more stable than cyclopentane. Okay, right. And here, is cyclohexane is existing in its planar form? No, it is existing in its suitable conformations based on the requirements of that particular organic structure. Okay, so we will see the conformations, so which are called as conformers. Okay, right. And how can you define conformation? So before that, steric strain, so simply repulsive interaction between adjacent non-bonded bulk atoms or groups considered as steric strain. So already we have shown that if the two hydrogens are eclipsed each other, they are small atoms, they contribute torsional strain only, torsional strain. But if we have two bulk methyl groups here which are eclipsing each other, in this case not only torsional strain, here another strain also takes its part, that we call it as steric strain. Okay, so whenever these two groups are completely eclipsed, highest strain belonging to steric strain. Okay, so that's why whenever the groups or atoms, if they increase their size, then they lead to steric strain. Okay, right. Now, to relieve a strain and to release energy to get the stability, cycloalkanes exhibit various conformations. Okay, right. So why the cyclohexanes are showing conformations? Because to relieve the extra energy from them to get the stability, they are showing different conformations which having low energy than their planar structures. or planar rings. Okay, right. And how can you define conformation or conformer? Here, the isomers, just take it, the isomers that differ, okay, that differ as a result of sigma bond. Okay, as a result of sigma bond rotation of carbon-carbon single bond. Okay, so whenever the rotation of carbon-carbon single bond leads to different isomers, and those isomers are considered as conformers. Okay, right. Now we are going to look at how those rings from 3-member to 6-member or 7-8-member rings, how they are existing in nature with their conformers. Okay, so here the basic point is almost all the rings are non-planar because to relieve their extra energy, they exist in non-planar structures and which are calling as conformers. Okay, right. Now just look at here, cyclopropane. Okay, so just remember that only the ring, the saturated organic ring, that is 3-membered ring, is almost planar. Okay, so all other rings can exist in non-planar structures. Okay, right. And here, as we said, the bond angle is 60 degrees. So high strain is observed in cyclopropane because of small, you can see the high deviation from that ideal bond angle, 109 degrees 28 minutes. So in this case, the cyclopropane is considered to have a bent-like bonds instead of a planar bond. Okay, here the bonds are not straight, so the bent bonds can be observed to increase the bond angle. So that is to decrease the difference from that by ideal bond angle to relieve some strain. The bonds in cyclopropane are just predicted to have some bent like bonds. Okay, so just remember that. And here, so here we can see the next case is cyclobutane. Just take it, cyclobutane. Right. So less angle strain than cyclopropane is observed because cyclobutane is having the bond angle 90 degrees. That's why less angle strain. Okay, and here, but cyclobutane experiences more torsional strain. So can you say why cyclobutane experience higher torsional strain than cyclopropane? The answer is whenever the number of eclipses increases, then the torsional strain increases. Now you can get it by just drawing these here. You can see, so 1, 2, and 3. Okay, 1, 2, 3. So you can see almost 6 eclipses. In cyclobutane, you can see almost 8 eclipses. Okay, so that's why here cyclobutane experiences high torsional strain than cyclopropane. Okay, so to relieve the ring strain, cyclobutane attains non-planar, a bent-like structure. You can see almost, we can say, a butterfly-like structure can be observed for cyclobutane. Now you can see the drawing here. So like this, the structure is observed. Okay, not much like this, and just wait. So like this, right? And just try to draw the hydrogens on each of the carbon. So here you can see that the hydrogens are out of eclipsed positions. That's why torsional strain is decreased in its bent or butterfly-like structure or geometry of that cyclobutane. By that, it releases some energy and it will gain some extra stability. Okay, right. And here is a question for you, the typical question. By just understanding the concept here on how the cyclobutane exists, you should answer this question. Okay, right. Now I'm just drawing the questions here. So two carboxylic acid groups are there, CO2H, CO2H here, and then A and B. Which one is the stablest one? Okay, so most of the students simply choose option B as the answer without looking at the basics of how the cyclobutane exists in the nature. Okay, so the answer is A, not B. You can understand it why. Because already we said that cyclobutane exists in bent-like structure where you can draw the structures here. The first one, cis. So try to draw it like this. Here is the CO2H and the CO2H. This is cis form. Okay, right. Now try to draw the trans form here. Now one is like this. Okay, one CO2H like this. If you bend this, you can see. If you bend here on these two carbons, you can get this structure. Now here the eclipse or steric strain can be observed on the trans, whereas in cis these two bulk carboxylic acid functional groups are away from each other and there will be no chance for any eclipses or torsional strain. That's why cis is more stable than a trans. Okay, this kind of questions you may expect in your examinations. Here we need to look at the basics. Okay, so we need to remind that the cyclobutane is not going to exist in its planar form. So here we need to try the bent structures, then you can get the answer easily. Okay, right. And next case we need to look at the cyclopentane. Right, here the cyclopentane. So in cyclopentane the torsional strain increases. So here in cyclopentane we know that bond angle or simply angle strain is less but torsional strain is high because number of eclipses increases in its planar structure. That's why cyclopentane can also exist in its non-planar structure. The most stable form of it is envelope-like structure. Okay, like this envelope-like structure where some torsional strain is decreased in this case, but not completely, but some of the torsional strain is relieved for this carbon. That's why cyclopentane exists in envelope. Okay, envelope-like structure. We can also see a twisted boat. So it is also observed in cyclopentane in some cases. Okay, but the most stable conformation of cyclopentane is envelope-like structure. Okay, right. And now the cyclohexane, which is most important for your competitive purpose, just focus on it. Okay, right. Now cyclohexane. In cyclohexane, bond angle is 120 degrees and eclipses are also increasing. Okay, 12 eclipses can be observed on its planar structure. That's why it is highly strained in its planar form. That's why it can exist in its conformations. The most stable conformation of cyclohexane is chair conformation. Okay, right. In the chair conformation, the hydrogens or just takes their positions as like that here. So axial, equatorial, equatorial, axial, okay, and axial, equatorial, here axial and equatorial. So here equatorial and axial. Just remember that, practice a number of times on chair-like conformations while solving the questions. Okay, so if you have the easiness on drawing the chair conformations and ring flippings, it will be very helpful for you in solving the questions on chair-like conformations of cyclohexane derivatives. Okay, right. Now, here, this stablest form, how we can say it is most stable? Because you can see all the hydrogens are out of from the eclipsed positions. They are not in eclipsed positions, and also each and every bond angle will be near to 109 degrees. That's why the chair conformation is the most stable conformation of cyclohexane. You can simply look at Newman projection, where you can see the how they are, that means hydrogens are not in eclipsed positions. Okay, right here CH2. Now just draw the hydrogens here. Okay, right, and in the next case you can draw CH2 here, hydrogens. Okay, you can see they are not eclipsed. That's why most of the hydrogens are just moved out from the eclipsed positions. That's why torsional strain is decreased in maximum. Okay, and also bond angle is decreased to the ideal bond angle. That's why chair conformation is the most stable one. Now, it is more important to know how the chair conformation exists in its isomeric form. Okay, right. Now just try to draw. Just have the patience. Just watch the video completely. Okay, right. HA here, and equatorial. Here equatorial. Here axial, equatorial, and axial. Okay. Now try to flip this chair conformation like this. Okay. When you flip it here, then I am going to give the numbering of the carbons. This carbon has 1, okay, this carbon has 1 and 2, 3, 4, like that. Okay, now this is 1, 2, 3. Now how the changes can be observed? The axial hydrogen just moved to equatorial position, and equatorial hydrogen moves to axial position. So you need to remember that when chair conformation, that means simply say ring flipping takes place. Okay, ring flipping takes place on conformations of cyclohexane. Axial groups or atoms become equatorial, and the equatorial groups or atoms or groups move into axial position. Okay, just keep this point in your mind. They will help you a lot in solving the questions on chair conformations of cyclohexane derivatives. Okay, right. And next case we need to look at some other conformations of cyclohexane. We know that already we said chair conformation, which is the most stable conformation of cyclohexane. Now we can also see a boat conformation. Okay, a boat conformation, where in boat conformation a flagpole interactions are observed. These interactions are called as flagpole. Okay, and some partial eclipses also observed, right? So that's why boat conformation is less stable than chair conformation, and here extra flagpole interactions leads to some strain. That means they increases the energy of that boat conformation of cyclohexane. That's why which is less stable than chair conformation. And here we can also see twist boat. So this is twist boat. In twist boat, the flagpole interactions are decreased or minimized, because by just twisting the boat, in these two hydrogens are moved away from each other. That's why in twisted boat, flagpole interactions are minimized, and also you can see the eclipses are decreased. Okay, some partial eclipses can be seen. In boat conformation, almost eclipses of these hydrogens on these carbons can be observed, but in this twisted boat, the eclipse, that means eclipses or just minimized, okay, by just twisting those carbons. Hence we can say twisted boat is more stable than this boat conformation. Okay, the first highest stability conformation of the cyclohexane is simply chair conformation, and second priority goes to twisted boat, third priority for this boat, and next another possibility is there as a conformation of cyclohexane, which is considered as half chair conformation. Okay, half chair conformation, and in this half chair conformation, most of the sp2 hybridized cyclohexanes, that is cyclohexanes, can exist in this half chair conformations in most of the transition states. Okay, right, and we can see some examples of these compounds, how they exist. Okay, can you give the example of boat? Okay, the molecule which exists in boat conformation. You may get the question, you may given with different options, you need to pick up the correct one. Here I am going to give the example for it, norbornane. Okay, so norbornane is the best example. So here you can see this is norbornane structure. You may get the confusion, how it is norbornane? It is completely front view. Okay, now just look at the side view. You can easily remember or remind it as norbornane. This is the side view. Okay, so norbornane existed in boat conformation. Now, can you give the example for twisted boat? Here, the example for the twisted boat here is, this is the example. We can call it as twistane. Okay, twistane is the example for twisted boat or skew boat structure. Okay, right. Now, can you give the example for chair conformation? Adamantane. Just take it. Adamantane is the example of chair conformation. So, this is the structure of it. So, this is adamantane. Okay, so these are the typical examples for it. Now, we are going to discuss substituted cyclohexanes, which are very important for your competitive purpose. Now we can start with monosubstituted cyclohexanes. Okay, right. Now just draw the chair conformation here, so we can deal with chair conformations more, because the most stable conformation of cyclohexane is chair. Okay, right. Now, so try to draw the substituent X in equatorial position. Okay, right. Now just flip it. Just flip this ring, and in this case, you can get this. As we said, axial groups, sorry, equatorial groups move to axial, axial group move to equatorial positions. That's why equatorial hydrogen will move to axial position here. Okay, right. For example, if all the hydrogens, okay, all are the hydrogens on cyclohexanes, if the cyclohexane is not substituted, then these two structures are having similar energy and they are same in stability. But if we take the substituent instead of hydrogen, any other group, for example, if you take methyl group here in this place, okay, now, so which is the most stable one? We can simply choose option A is the most stable one, because this CH3 doesn't experience any steric interactions. Okay, you can get it here. I'm just trying CH3. Now here just draw the CH3 here. Okay, now so just draw CH3 here. You can see the interactions with those hydrogens. Okay, these interactions are called as 1,3, okay, diaxial interactions, right? And we can also say a 1,3 strain, that is axial 1,3 strain, right? So these strain increases energy for this conformation. That's why conformation B is less stable than conformation A. Okay, right. And now, so next case, we need to look at another examples of the that means we need to go for the disubstituted cyclohexane. So just remember that whenever the cyclohexane is monosubstituted, the equatorially substituted chair conformation is more stable than axially substituted chair conformation, because 1,3 diaxial interactions increases the strain, and which increases the energy in that conformation, leads to less stable chair conformation of it. Okay, right. And next we need to look at the disubstituted cyclohexanes. So disubstituted. Right. Here we can start with 1, 2. So cis, okay. Just say X here, X. We can say 1, 2 cis disubstituted cyclohexane. I now try to draw its chair conformations. Okay. So here, these are very important. You may expect questions from disubstituted cyclohexanes in many or in chemistry competitive examinations. Okay, right. So X here, X. Now you can see whenever the groups which are cis to each other at 1, 2 positions on planar cyclohexane, or just move into equatorial, axial or axial equatorial positions on their respective chair conformations. Just listen carefully. Okay, whenever we have given with chair in planar cyclohexane with the two substituents at 1, 2 positions in cis relation, then when we convert it into its chair conformation, those substituents move into equatorial axial or axial equatorial positions. Okay, right. And here, can you decide which is more stable? So simply, both of the conformations experiences same. Okay, here two diaxial interactions. For this, here two diaxial interactions. That's why these two conformations are equally stable or equally energized. Okay, right. And next case, next possible way. So one is above the plane, one is below the plane of the cyclohexane. So we can call it as 1, 2 trans, right? So for this, just draw the two isomers of chair conformations, possible isomers here. X, just take it CH3. Here is the CH3. Sorry. Right. Right. CH3 and CH3. Now you can see that in first conformation, we have two methyl groups axial position. For when you flip this ring, you can see two methyl groups should move into equatorial positions. Okay, that's why here 1, 2 trans disubstituted cyclohexane in its chair conformations produces axial relationship or equatorial relationship in its conformation, respective conformations. Okay, right. So like this we can apply, or we can make a table which is very important, and just note them. Okay, now 1, 2 cis groups will give equatorial axial or axial equatorial relationship. 1, 2 trans cyclohexanes in its chair conformation, just take it chair conformation, here planar cyclohexane, right? They will give axial or equatorial relationship. Okay, now just try to take 1, 3 cis, which leads to equatorial axial, equatorial or axial in relationship. 1 comma 3 trans, so which gives equatorial axial or axial equatorial relationship. Now 1 comma 4 cis, which give equatorial axial or axial equatorial. 1 comma 4 trans will give axial or equatorial. Just remember this table, then you can solve many questions on disubstituted cyclohexane derivatives. Okay, right. And next, so the question, after understanding the table, how the groups move into their respective positions on cyclohexane chair conformation, try to answer this. So here we need deep analysis of the concepts. Okay, it is not important to just understanding the concept. We need to have the ability to apply those concepts on solving the problems. It is only that means this ability will increase for a particular candidate or aspirant when that aspirant practice more and more problems. Okay, so the practicing is very important here. Now I can here are the options: chair, second one boat, and third one twisted boat. Okay, and fourth one I can say so half chair. Right, the question is the most stable, okay, the most stable conformation of the given structure is. So which one is the correct one? Which one you can choose? Okay, so here we need to apply, or we need to try the all those conformation. Just try to look at the chair conformation, how it will give. So it is 1 comma 3. Okay, so 1 comma 3 trans. Already we have seen that 1 comma 3 trans will give equatorial axial or axial equatorial relationship of these bulk groups on its chair conformation. Okay, right. Now I'm going to give one is equatorial. Always we should give the bulkiest group equatorial in the first step. Okay, and after it is equatorial, another group must be axial in its third position. So just take it as the third position, and here is the axial group. You can see a bulk 1 comma 3 diaxial interactions can be observed. That's why chair conformation is not the stablest one, because steric here we can say high or strong steric repulsions can be observed through 1 comma 3 diaxial interactions or A1 comma 3 strain. Okay, right. Now try to look at the boat conformation. Here is the boat. Right, in this boat conformation you can see the two groups are trans to each other. So here 1 comma 3 positions, right? For example, one bulk group is taken here. Okay, one must be equatorial. Now 1 2 3, or you can take 1 2 3. In these three cases you can see that one group must move into the position where strong steric repulsions can be observed with those flagpole interactions. That's why we can simply remove boat conformation, right? I now just look at twisted boat conformation. There, just twist it. Okay, right. Now this is the twisted boat. You can take one equatorial and one group like this. So due to the twisting, here you can see those bulkiest groups are completely move away from the flagpole interactions. That's why it is the most stable form. Just remember that half chair is absolutely nonsense here, because half chair is the least stable conformation of cyclohexane, and which cannot afford these two groups at perfect positions in half chair. Okay, so here answer is twisted boat. Okay, right. And next question I'm going to give. So if you listen carefully, if you listen the basics carefully, if you have the command and basics, the answering is very easy. By just analyzing the questions, you can give it. Okay, now just take the another example. Here we have taken trans CH3, here CH3, right? So 1 comma 2 trans, planar cyclohexane. When you convert into respective chair conformations, they must be equatorial or axial in relationship. Okay, so here just draw CH3 and CH3. Now just flip the ring here, and if you do that, you can get this. One is axial, one is axial. CH3 here, CH3 here. Which one is the most stable? By just looking at the diaxial interactions, we can say that A is more stable than B, because here we can see only one Gauche interaction. This interaction is considered as Gauche interaction, CH3. Okay, already we have seen in starting of the lecture, the Gauche type of interaction leads to increase in 0.9 kilocalorie per mole energy to this conformation. Okay, and there are no diaxial interactions. That's why this conformation is having only 0.9 kilocalorie per mole of energy. Now just try to look at the second conformation B, where you can see the diaxial interactions, one with this hydrogen, one with this, and here one with this and one with this. So total you can see two diaxial interactions can be seen. Okay, so that's why here energy is simply 3.6 kilocalorie per mole energy. So highest energy is absorbed in this chair conformation when we compare with equatorial conformation. That's why we conclude that equatorial relationship on chair conformation of 1,2 trans-cyclohexane is more stable than axial substituted cyclohexane chair conformation. Got it? Okay, and then now you can go to the next example. Try to answer this by just understanding the concept. Okay, so here just take this A and this is B, right? Now just take this C and the next case D. Okay, and I'm going to give another example. So here is E. The question is, which chair conformation is more stable? Most of the aspirants simply choose option A as the correct answer, and that is the correct one. Okay, and my question is, which is the least stable? So here we need to work. Okay, work on it, which is the least stable. Okay, so here as we said, the first one is more stable because two groups at 1,4 positions are completely equatorial. There will be no interactions are observed. That's why it is the most stable. And second stable one, which is the most second stablest one here, we can go with the E, because these two groups are equatorial in positions at 1,2 position. Okay, and in these equatorial positions, some Gauche interaction is only observed. That's why this is the second most stable chair conformations in the given options. Okay, and right, and the third case here, one is equatorial, one is axial. So only one axial group is there. That's why B is the third most stable one. And if you look at C and D, here this methyl group and this methyl group. So here we have two. These can experience 1,3 diaxial interactions, and which is most stable in between C and D. So here we need to look at, just try to check these. Here we have hydrogens. Okay, this is CH3, right, and here we have CH3, CH3. Here is the hydrogen. You can see the diaxial interaction is between methyl group and hydrogen. Okay, methyl group and hydrogen. Whereas here in D, we can see one is direct methyl diaxial interaction. We know that the bulk groups or leads to highest energy, or they import or they increase highest energy when we compare with CH3 hydrogen interactions. Already we have seen in the first slide. Okay, in starting of the lectures we have given the energy in kilocalories and in kilojoules per moles. Okay, so in that consideration, we can say that highest energy is absorbed in option D due to the direct methyl-methyl diaxial interactions. Okay, so that's why the least stable one here is option D, not C. Okay, now what is the correct order? 1, 2, 3, 4 and 5. Okay, so this is the way you can give the answer for it. Now next, the best example I'm going to give. So try to find the answer on it. Okay, here we have OH and here we have OH, that is 1,3 cis substituted cyclohexane, right? And the question is, which is the most stable chair conformation? Okay, right here. So the two hydroxy groups must be equatorial, right? Equatorial or axial. Now just try to draw the next conformation or isomer of it. Right, in this case you can draw. So when you move it, here is the hydroxy group and here is the hydroxy group, right? So you can see that whenever two hydroxy groups are there is the possibility of hydrogen bonding that will leads to the highest stability. Okay, just try to draw axis in here. You can see the hydrogen bond is possible. Whenever the hydrogen bond is possible, this axial chair conformation is more stable than the equatorially substituted chair conformation. Okay, so whenever hydrogen bonding is possible, the axial chair conformation will be the stable one. Okay, right. And next question here. So we have two hydroxy groups at 1,4 position, 1,4 cis. Right. The question is chair, boat, second one twisted boat, third one half chair. Which is the most stable conformation of it? Okay. Now the most stable conformation for this boat conformation. How can you say that? Because if the two hydroxy groups are in flagpole position. Now okay, just wait. I will draw it in the best form. Okay, so here is the hydroxy group. Okay, and here is the hydrogen. You can see the possibility of hydrogen bonding. Whenever hydrogen bonding is possible, the flagpole hydroxy groups or having the hydrogen bonding leads to highest stability for this boat conformation. So the boat conformation is the most stable among the all given conformations of 1,4 cis substituted dihydroxy cyclohexane. Okay, right. And then the next question. These are the very typical examples. You may get the questions on them. Okay, right. So that's why I'm just giving here. So if you are interested, you can visit and join CHEMMasters.online website, where you can get the best concept oriented courses and where you can practice very high standard online test series. Okay, and to get the success by just practicing them, I can assure you that you can solve the very difficult questions in your main examinations. Okay, so try to find the website and try to join the courses. Okay, right. Now just take the example here, bromine. So here is the bromine. Okay, 1,2 trans disubstituted cyclohexane ring. Right, here we have two structures, bromine, that is axial in relationship, and next one equatorial. Okay, so just give its confirmation. Right, bromine here, these two are equatorial in relationship. Okay, right. Which one is more stable? In simple cases we can go with option B, but when you consider solvent plays a major role here in deciding which conformation is the most stable and which exists in the solvent. Okay, right. Now just to check how it can give. So here the bromine is more electronegative, That's why dipole vector just moves towards the bromine. Right here you can see, due to the presence of two bromines in axial positions, the dipoles are completely minimized here. So dipole moment will become 0, okay, almost 0. So whenever dipole moment is 0, this chair conformation exists in apolar, or we can say non-polar solvent. So in non-polar solvent, A is the predominant chair conformation. Okay, right. And now just look at the second conformation B, where the vectors are not just cancelling each other. That's why dipole moment is not equal to 0. So this conformation has a dipole moment, and it will exist in polar solvents. Okay, in polar solvents, conformation B is the predominant one over conformation A. Okay, right. And try to watch the second part of the cyclohexanes in 60 minutes, where you can get and most typical examples on and analysis of it. Okay, so thank you very much, and please subscribe the channel for more updates, and like the video. And if you're interested further, you can visit and join an website to get the best concept oriented courses along with high standard online test series, and we will be available 24/7 to help you in solving the doubts and in encouraging you towards your success, and how to we can guide you how to prepare. Okay, so thank you very much.